Welcome to Review Lecture 5.2, Kirchoff's Rules. Upon completing this, you should be able to use Kirchoff's rules to analyze complex circuits. First one of Kirchoff's rules is a junction rule. A junction is a point where three or more wires meet. So out equals in. So a summation of all the currents coming in has to equal the summation of all the currents leaving the junction. This is a consequence of conservation of charge. Actually, it's conservation of mass energy. The fluid analogy to this is the flow of water into a junction equals the flow of water out of a junction. And the units on the junction rule are amps. The alternative version is if you call current in positive and current out negative, then the sum of the currents in a junction is zero. Another word for junction is node. If you go completely around any closed loop in a circuit, the sum of the potential changes equals zero. Sign matters here, and we'll talk about the sign rules in the next slides. This is a consequence of conservation of energy and the definition of equal potential. And why does it equal zero? Well, you're coming back to the same place. And it's a conservative force, so you can't have two different potentials assigned to the same location. Now, the units on the loop rule are 1 amp ohm equals 1 volt. That just comes from V equals IR. The alternative version for this is when you traverse this complete loop, the sum of the potential increases equals the sum of potential drops. Now, if you go partway around a loop, the sum of the potential changes equals the potential difference between those 2 points. This can be used to find the potential difference across components of or parts of a circuit. Now, here are the sign rules, the resistance sign rule. Now, the way I like to look at resistances is they're kind of like a waterfall. You've got current flowing through them. When you go in the direction of the current, the water flows down the waterfall. So you go from a higher potential to a lower potential. The sign on the potential change is negative and delta V equals minus IR. When moving through a resistance opposite to the direction of conventional current, the potential rises. This is like moving upstream and climbing up a waterfall. The sign on the potential change is positive and delta V equals positive IR. The EMF sign rule is when you go through an EMF device from the short, which is the negative end, to the long, which is the positive end, the potential increases. You're going toward the positive terminal through the battery. So the charges have then been pumped up and gained energy. So delta V is positive E. The easy way to remember this is if you go toward the positive terminal through the battery, the sign is positive. When you go in the opposite direction, so in other words, you're going from the positive to the negative terminal through the battery, the potential then decreases. This is the opposite to the usual direction of conventional current flow in a discharging battery. So delta V equals minus E. So going toward the negative terminal gives you a negative sign. Very easy to remember these, and yet this is where people screw up. Example is a simple one-loop circuit where we have a real battery which has an internal resistance, little r, and it's connected in a circuit with a load resistance, big R. We're going to find the current I in this simple circuit. Now, the internal resistance of the battery, of course, as we mentioned before, is the electric resistance of the conducting materials of the battery, and thus is a permanent feature of the battery. We're going to find the changes in electric potential around the circuit. We're going to apply the loop rule, and it's our choice. We can pick any place to start. We can pick any direction. Doesn't make any difference. I start at point A, and I'm going to go clockwise. So I'm going to start here, and I'm going to go from the negative to the positive terminal through the battery. That's positive E. I'm going to go with the current through this internal resistor. That's down the waterfall, so minus I times little r. I'm going with the current through big R, down the waterfall, minus I times big R. I come back to my starting point. This is an equal potential surface. Voltage is equal to 0. Then we can solve for I. I equals E over the sum of the resistances. E over R plus big R plus little r. Now, I can also always check this by going around in the opposite direction. In this case, I decide not able to start at the same point. Doesn't make any difference to start any point. It's completely arbitrary. I'm going to begin at the positive plate of the battery, and I'm going to go counterclockwise. So in this case, I'm going from the positive to the negative terminal of the battery, that is minus E. I'm going against the current flow but through the big resistor, so it's plus IR. I'm going up the waterfall. I'm going against the current or up the waterfall through the little internal resistance, so that's plus IR. I've come back to my starting point, and that is 0. Then I equals E over the sum of the resistances. And I came up with the same equations. Now, the only difference between this equation, this one right here, and this equation is that if you take this one and multiply through by -1, you'll get that one. So this is a good way to check this. Because where people screw up on this is they either forget something or they switch a sign. If you go both ways, you're not so likely to make that mistake, or you're least likely to catch it. Now we're going to have a single loop circuit with 2 real batteries. Okay, the EMS and resistances in the circuit are E1 is 4.4 volts, E2 is 2.1 volts, R1, which is this internal resistance, is 2.3 ohms, R2, which is this internal resistance, is 1.8 ohms, and the big resistor, or the load resistor, is 5.5 ohms. What is the current of the circuit? What is the potential differences between the terminals of this battery? In this case, they have told us the direction of the current. However, even if they hadn't, we could make an educated guess. Remember a long time ago, I told you that when you have a battery which has a higher potential, and you have a circuit with another battery that has a lower potential, the one with the higher potential is going to be charging the lower potential one. Well, in this case, that means this battery, E1, is going to be charging E2. That means the current is going to be clockwise in this circuit, where this battery is discharging itself to charge up that battery. What is the current of the circuit? I, the circuit. What's the potential difference between the terminals of battery 1? Physics of this is a Kirchoff's rule problem, and we still have Ohm's law, V equals IR. Okay, so I write down the knowns and unknowns. E1 equals 4.4 volts, E2 equals 2.1 volts, R1 is 2.3 ohms, R2 is 1.8 ohms. The big resistors, the low resistors, 5.5 ohms. We need the current, and we need the potential difference between A and B across this first battery. We apply Kirchoff's loop rule. I decided to start at point A, which is right here, and decided to go counterclockwise. I don't know why, it just did. Okay, so in this case, I'm going from the positive to the negative terminal, so it's minus E1. I'm going against the current, that's up the waterfall, so it's positive IR1. I'm going against the current, that's up the waterfall, so it's positive I times big R. I'm going against the current, up the waterfall, so it's positive IR2. I'm going from the negative to the positive plates, so it's plus E2. I've come back to my starting point, and that means it's equal to 0. The units on that is 1 amp ohm equals 1 volt, and I check and make sure. Yep, they're all right. Then I can solve for I. I will be E1 minus E2, or the sum of the resistances, big R plus R1 plus R2. Now notice, remember the current is the voltage divided by the resistance. So this is another way of checking that. You can use the units in Ohm's law to make sure you got this right. Now I put my numbers in here. So I will be 4.4 volts minus 2.1 volts divided by 5.5 ohms plus 2.3 ohms plus 1.8 ohms. Ends up being 2.24 amps. And I guessed right, battery 1 is charging battery 2. Now I want to find VA minus VB. Now, I have 2 choices here. I can either go around this part of the circuit or go around this part of the circuit. It turns out this is easier because here I have 2 resistances and 1 potential. Here I have 1 resistance and 1 potential. So the easiest one is through battery 1, and I know everything about battery 1. So I start right here, and I start with VB, and I'm going with the direction of current through this internal resistance here, so that's down the waterfall. So that's minus IR1. I'm going from the negative to positive plate. So that means the battery is pumping up the charges, so it's plus E1. And now I come to VA. So here's my equation to determine the difference between VA and VB. I've used part of Kirchoff's loop rule. The units on this is a units check, 1 amp ohm equals 1 volt. Looks like the units are good. Now I can solve this for VA minus VB. When I do that, it ends up being E1 minus IR1. At this point, I can plug my numbers in. 4.4 volts minus 0.24 amps times 2.3 ohms. Units check again comes out good. VA minus VB equals 3.8 volts. Now I can go through the other part of the loop as a check. Start at VA, and I'm going with the current, and I'm going from the positive to the negative plate through this battery, so that's minus E2. I'm going with the current through R2, so that's down the waterfall, so minus IR2. I'm going with the current through the big resistor, that is minus IR, in other words, down the waterfall, and I've come to VB. And I can solve for VA minus VB as I did before, and this time it comes out E2 plus I times the quantity R2 plus big R. And again, I do the units check, and the units come out okay. Now I'm going to solve for VA minus VB, plug the numbers in, and when I do that, I wind up with a slight difference. Now the last digit is uncertain. The difference here is due to round off. How to use Kirchoff's rule? Assign labels and symbols. It's a good idea when you have a resistance R1 and you have to pick a label for a current, call that I1. Okay, try to make sure that that your symbols sort of match, the currents and the potentials and everything kind of match, because it'd be a lot easier. Also draw the circuit and label everything. Assign a direction for each current. It's okay to guess, but don't change this in the middle of the problem. Generally, currents will be the unknowns. Count the number of unknowns. You will need that many independent equations. Identify each loop and apply the loop rule for each loop. You can pick any direction or starting point, but go completely around the loop. Remember the sign conventions for resistors and EMFs. Also, the loop rule will be in terms of potentials, because that's what it's written in. Identify the junctions. Write the junction rule for junctions. The junction rule deals with currents. At this point, you will possibly have some extra redundant equations. Put those aside. Pick the same number of independent equations as you have unknowns. Solve for the unknowns, plug in your numbers, check the results, check the units. Did you answer the questions? Did you find all of the unknowns? If any of the currents comes out negative, you guessed the direction incorrectly, but the magnitude is okay, so don't worry. Do not do it over. If you do, you'll chase your signs forever. So here's another example, handling multi-loop circuits. So here's a multi-loop circuit. We're going to derive 3 independent equations for the multi-loop circuit. Okay, so what we do, and it's your choice. I decided to pick the left-hand loop in the counterclockwise direction, beginning at point B. I'm going to go from the negative to the positive terminal, so that's positive E1. I'm going with the current, that's down the waterfall. So that is minus I1 R1. I'm going against the current in R3, that's up the waterfall, so that's positive I3 R3, back to my starting point, equals 0. Units check, 1 amp ohm equals 1 volt. So I probably did that correctly. I'm going to go around this loop in the counterclockwise direction from point B. I go with the current through R3, so that's minus I3 R3. I go with the current I2 through R2, that's down the waterfall, so that's minus I2 R2. I go from the positive to the negative terminal through this battery, so that's minus E2. I come back to my starting point, that means I'm equal to 0. The units check, okay, amp ohms and volts, good. Now I'm going to apply the loop rule to the big loop. I'm going to move counterclockwise from point B. I go from the negative to the positive terminal through E1, so that's positive E1. I go with the current down the waterfall through R1, so that's minus I1 R1. I go with the current down the waterfall through R2, so that's minus I2 R2. I go from the positive to the negative plate through E2. So that's minus E2. That equals 0. Check the units. 1 amp ohm, 1 volt. Probably got it right. Apply the junction rule at point B. Okay, the outs equal the in. I have I1 and I3 going out, and I have I2 coming in. So I1 plus I3 equals I2. The units on that, amps. Assuming you know the values for EMFs and the resistances and don't know the currents, there are 3 unknowns here and 3 independent equations. The 4th equation is not independent, but it can be used to check on the results. Now, again, if you don't know the direction of a given current, just guess. If it comes out negative, the magnitude's okay. You just have a sign. Don't worry about it. Don't change anything. Just leave it alone. Okay, now we have 2 batteries. They have unequal EMFs of E1 of 2 volts and E2 equals 3 volts. They're connected as shown. If each internal resistance is 0.1 ohm and big R, which is the load resistor, is 4 ohms, what are the currents in each branch and what is the voltage across battery 1? First thing I do is write down my knowns and unknowns. I know E1 equals 2 volts, E2 equals 3 volts, the internal resistances are 0.1 ohm. The big resistor is 4 ohms, and I need to know VBA. And that, by the way, this potential across here is the same potential across this resistor, so that might make it easier to find this. Once I get the current in this branch, I know that. Okay, the physics of this is a Kirchoff's law problem. I decided to do the junction at B first. I guessed all the currents, by the way, here. I picked this one going that way, this one going that way, and this one going this way. Apply the junction at point B, and then I have this current coming in, that's I, and that is equal to the sum of the currents going out. So I equals I1 plus I2, and the units on that are amps. Good, I've got the right units. Now I'm going to go through the upper loop in the assumed direction of I, which is counterclockwise. And I decided to start right here. So I'm going with the current down the waterfall. So that is minus big R times I. I'm going from the negative to the positive plate through the E1. That is positive E1. I'm going with the current through the internal resistance down the waterfall. That's minus RI1. I've come back to my starting point, so that equals 0. The loop rule, the units have to be amp ohm equals volts. Yeah, amp ohm volts. Okay? Now, normally I don't suggest that you plug numbers into things, but this is one time when you might want to do it. And keep units on stuff. So I have minus 4 ohms times the current I. I have plus 2 volts, which is E1. I have minus the 0.1 ohm times I1. Again, I check the units, make sure they're all right. Yes, good. Looks like the unit's okay. Now I'm going to go through, and I have 2 choices. I can go through this loop or this loop. I just decided to pick the big loop. I'm going to start with E2, and I'm going to go counterclockwise in the assumed direction of I2. So I started right here, and I'm going from the negative to the positive plate, so that's positive E2. I'm going down the waterfall through this internal resistance, so that's minus R times I2. I'm going to go down the waterfall in the assumed direction of the current through the big resistor, so that is minus R times I. I've come back to my starting point, so that equals 0. I check the units. I've got amp ohms and volts. Good. Now I put the numbers in. I have 3 volts for E2. I have minus 0.1 ohm times I2. I have minus 4 ohms times I. Again, I check the units. They're good. This is a system of 3 independent equations. I can solve it. When I do that, I will equal 0.6138 amps. I1 is negative 4.6914 amps. I2 is positive 5.3086 amps. This just means I guessed the current incorrectly on I1. So I1 is actually going in the opposite direction. Now, the easiest way to find the potential across battery 1 is through the resistance R. And then we just use V equals IR. 0.6173 amps times 4 ohms times the units conversion here, 2.47 volts. Now, comment, battery E1 is actually being charged because the direction is going this way. I probably could have guessed that. Okay, E2 has a greater potential than E1, so this one has a higher potential than that one, so this one's going to charge that battery. I probably could have done a better job of guessing the current, but it doesn't hurt anything. I don't care. I'm not going to sit there spending time doing that if I don't have to. Now, which of the equations is valid for the circuit below? Now, there's several different ways you can do this. You can eliminate the incorrect ones. I usually do is I start with them and just see if they make sense. Okay, so what I'm going to do is I'm going to start with this one. And whenever you see numbers by themselves, they're batteries. When you see a number like you see a current, that's a resistor. So there's a tip there. So I see this 2 volts, that's this battery, and looking the sign on this, it's going in this direction, from the negative to positive plate. So I start here, and here's I1, and I come to this resistor here, okay? And I'm going down the waterfall in the direction of current. So this is looking good, all right, minus I1. Now I have to decide something here. I see a minus 2I2, okay? That could be this. But I'm missing something. I'm missing this 4 volts, so this one's incorrect. I can eliminate that one. I'm eliminating crap is what I'm trying to do. Now I go to the next one. I see this 2 volts here, so that's probably this battery here. Okay, I see minus 2I2, or minus 2I1. Well, that one can't be. There is no 2 ohms here. There's no way I'm going to get 2 ohms out of I1, so 2 is crap. I go to 3. I start with the 2 volt battery again, and I see minus I1. That's looking good. I'm going from the positive to negative plate, so that's minus 4. I'm going down the waterfall, so that's minus 2I2, and I come back to my starting point. 3 is good. So this is probably the correct answer, but always check to make sure. I go to number 4 here. I see I3. Okay, that looks like that is going through here, right here. Here's a 1 ohm resistor, so that would be I3. Okay, and then I see minus 4. Okay, that is not going to work. Well, that part could work because it doesn't have to go in the same order. So it's probably this loop here because you can write them out of order. Okay, it makes it kind of tough. Minus 2I2. I'm going with the waterfall, but I'm going plus 6, and there's something missing. This 3 ohm resistor is missing in here. So 4 is incorrect. Okay, 5. I'm going 2 minus I1, 3I3. Okay, minus 3. I'm going in the wrong direction there. That would be positive 3I3, so 5 is incorrect. So the correct answer to this one is 3. So equation 3 is valid for the left loop. If I move counterclockwise through the left battery, I end up with positive 2 volts. Then there's a drop through the 1 ohm resistor with the current I1 flowing. Then we go through the middle battery here, the 4 volt battery, but we're going toward the negative terminal, so it's minus 4. So, and then finally there's a drop through the 2 ohm resistor with I2. So I eliminated number 1 because it includes I1 and I2, so it's a left loop with the 4 volt batteries missing. I eliminated number 2 because it includes all 3 currents. No loop has all 3 currents. I eliminated number 4 because it includes I3 and I2 and the 6 volt and 4 volt batteries, so it has to be the right loop, but the coefficient on I3 is incorrect, and magnitude and sign it should be minus 4I3 or minus 1 plus 3I3. I eliminated number 5 because it includes I1 and I3, so it's the large loop that is missing the 1 ohm resistor in the upper right-hand corner, and also the negative sign on I3 should be positive. Actually, it should be positive 1 plus 3, I3 equals 4I3, because you can condense these. Okay, so I decided to correct them all. The left loop, starting counterclockwise, starting at the 2 volt battery. This is 2 minus I1 minus 4 minus 2I2 equals 0, and we can condense that to minus 2 minus I1 minus 2I2, or in reverse, just change all the signs. The right loop, which is starting at the 6 volt battery, going clockwise around at the 6 volt battery. So it's positive 6 minus 3I3 minus 4 minus 2I2 minus 1I3. And we can say that as 6 minus 4I3 minus 4 minus 2I2 equals 0, or 2 minus 4I3 minus 2I2, and then we can reverse it too. The large loop, we're going to start at the 6 volt battery. So, and we're going to go clockwise. So we're going positive 6 minus 3I3 plus 1I1 minus 2 minus 1I3 has to equal 0, and we can condense some of that 4 minus 4I3 plus I1, or in reverse. Now, this is a good place to practice. And so if you need practice doing this, I gave you as many different ways to do this as is just about possible. You're analyzing a complicated circuit and one of the currents comes out negative. What does it mean? The current's reversed, you just guessed wrong. Don't go back and redo the problem. Thank you.